live, and are there any questions before we get started today?
Hi, Professor. This is Sai here.
Yeah, hi.
So, can we just have a brief discussion about fourth question in the assignment? Like, I had a lot of confusion there. So, I already submitted the assignment. So, just in case if everybody has submitted, is it possible to have a short discussion for around 5 minutes or so?
Yeah, so uh, yeah, definitely. So about question 4 specifically.
So, I mean, it is very clear that one of the equilibrium solutions is all of them being zero, like
Mhm.
S, I, R, and B equal zero. But when you ask this to find other equilibrium solution, like, are you asking us to choose one of the terms as the independent variable and express all other uh, variables in terms of that independent variable, or what exactly is expected? Is a bit of confusion there. So
Yeah, definitely. So yeah, so now that we're all set. So let me just yeah, let's go through this because I think it's definitely worth talking about. Sorry, let me bring up the exact wording here. Yeah, right. So what we had, so 4. So what we had here, right, is S prime equals minus A B over K plus B times S plus D times R. I prime equals AB over K plus B times S minus R times I. B prime equals B times and B CI, and R prime equals R times I minus D times I. And so we want to find the equilibrium solutions. So in particular, that's going to be where this equals 0, this equals 0, this equals 0, this equals 0. So yeah, so as you said, of course, there's kind of like a first sort of obvious one, which you can just think of as like, well, what if there's just nobody who's sick, right? If I equals 0, then okay, then everyone's susceptible eventually, right? So that's the equilibrium solution. But of course, that doesn't actually restrict the population, right? So for any initial value of S, if there are no infected and no, so one solution is going to be that S takes on any possible value and I, B, and R are all 0. But let's actually derive that. So basically these, I'm going to call 4. So 3 and 4 basically allow us to express B and R in terms of I. So 3 implies that what? B equals EI over minus EI over NB, and 4 implies that R equals Ri over D. So then we can plug this into, let's say 2, for instance. So this is going to give us A times.
Professor, I think algebra is clear here. I mean, I just wanted to know if expressing I in terms of S, is that what is expected here?
Right. So there's two. So there's a non-trivial solution now is the big thing.
Okay.
Right. So and let me just push that through really fast. So what EI over NBS minus RI. This is supposed to equal. Sorry. EI over NB over K plus EI over NB. Okay. And so you can see when you multiply this out, you're going to actually get a quadratic expression. Right? You're going to get A minus A E over NB SI minus RI times K minus EI over NB equals 0, right? So there's actually two families of solutions here. There's I equals 0, in which case then S is whatever S happens to be. So S naught. And the other family of solutions is when you factor the I out, right? So S is going to be some big pile of parameters, right? Factor out I, and then you get some non-trivial expression in terms of S. And so those were the two families of solutions that I wanted to see. And once you get this this non-trivial answer in terms of S, right? So this is basically going to be this minus this equals 0. Then you can re-express I in terms of this, and you can re-express everything else in terms of it. Oh, sorry. So you're going to get a non-trivial relationship between I and S. Yeah.
Thanks for the clarification. Yeah, this is what
Okay.
we assume. Yeah.
Good. Okay. Fabulous. Yeah. And that was yeah, and I apologize because I said parameters in here because I was kind of, I was trying to keep things a little, explore it yourself. And so, of course, I was kind of thinking of the S nod and the I nod as the parameters. But I think that made it very unclear. I think that it was clearly implicated that by parameters I meant these guys. And so, yeah, I apologize for any confusion there. Any other questions? So that means different values of I would make S have one trivial. No, so actually it turns out that, yeah, so this, you actually get a pretty explicit, I mean, you get something that's basically like AI plus D. You get a pretty explicit expression. So different values of I, oh yeah, yeah, so different values of I, yes, sorry. Yeah, so when I is non-zero, you get this expression. And when I is equal to 0, then additionally you get this expression, which, I mean, essentially is the same. It's just that you're equating the D with the S non. Cool. Yeah, so by trivial, and I kind of tried to use trivial in quotes and say it because of course these solutions aren't trivial, right? But there's one solution where just about everything is 0, and that's what I was kind of calling the trivial solution. But I can understand your confusion because it is not actually a trivial solution, right? In fact, it's a family of solutions, all of which are non-trivial. So Yeah, I apologize for the confusion there. Okay. Any other questions about this or anything else on the homework? All right. Fabulous. So, all right. So today we're going to start talking about systems of everything set up here. Today we're going to start talking about systems of nonlinear differential equations. Change back to the more formal black. And in general, we're going to understand these in a couple of different ways. So one way, of course, and one of the tools that we already have available to us is understand them numerically, right? We can basically, we can go through and we can just simulate them using, whatever numerical software we have available to us. Another way of understanding them, though, we want to get some sort of heuristic picture understanding. And so one of the ways that this is done is through solution space analysis. Another, so basically we're going to sort of make some very rough assumptions about the derivatives, basically just the sign of the derivatives, and draw a sort of cartoon picture of the solution space. And it's a very good first pass for how to understand the general behavior of these things. We'll then talk about equilibrium points and do the careful equilibrium analysis, and that will then feed in to the linear systems analysis that we did last time. Just because, it's calculus. It turns out, of course, that when we're close to an equilibrium solution, then we're sort of effectively close to a linear system. Okay, so let's look at solution space and trajectory diagrams. So let's start with an example. Let's return to our favorite, one of my favorite sets of systems of differential equations. We have dx dt equals, in this case, let's use minus ay, dy dt equals ax. So if you remember, this is basically, going to be a scaled version of our spinning system, right? So here's roughly what our analysis is going to look like. So first, find the equilibrium points. Second is going to be to find the null clines. So, null clines. That is curves where x prime equals 0 or y prime 0. And 3, between each null cline, determine the rough direction of the trajectories. Determine the rough direction. The solutions. Okay, so in this case, what is the equilibrium point? So there's a single equilibrium point. So the equilibrium points, again, are going to be when x prime equals 0 and equals 0. So in the system of equations above, what is the single equilibrium point? After question 4, I'm assuming that nobody's answering because this is trivial. Yeah, exactly. Right. It's just a 0, 0 in this case. So x, y is 0, 0. And so we also want to look at the null clines. In fact, it'll for any linear system, it'll always be 0, 0. So the null clines here are going to be, so we have the x prime equals 0 null cline, which is just, well, okay, when x prime equals 0, y equals 0, and the y prime equals 0 null cline is, well, okay, when y prime equals 0, we must have x equals 0. Pretty straightforward in this case. And so then let's summarize this information. So we got this. So we have our equilibrium point. Actually label my axes. And then in this case, the null clines are like pretty trivial. They are, so we have the y null cline, and we have the x null cline. And so then what we said is our prescription for drawing this sort of cartoon picture is that within each of these regions, so let's call them, well, we can go with our conventional region notation. So for each of these regions, 1, 2, 3, and 4. Sit over here. We want to determine the rough trajectories. And so basically what we actually just want to determine is whether x prime and y prime are positive or negative. So for each region, is x prime and y prime greater than or less than 0? Okay, so let me just box the equations here again. X prime equals minus a y, y prime equals x. And so in region 1, we're going to have, okay, so in region 1, y is positive, and so x prime is equal to, well, let's assume, sorry, assume that a is greater than 0. So then y is something positive times something positive times a negative. So we're going to have x prime is less than 0. Y prime, on the other hand, well, x is also going to be positive in region 1. And so this is going to be, we're going to get that y prime is greater than 0. If you want, you could represent this as minus plus, just for sort of simplicity. And then the kind of standard way to represent this is by saying, well, x is decreasing. So if we have a solution, right, and we are starting at some point in this region here, anywhere in region 1, then the solution is decreasing in the x direction and increasing in the y direction. So the rough trajectory is like that. Okay. Any questions about that? So in region 2, so over here now x is negative, y is positive. So what are we going to get? X is negative, so well, x prime is less than minus ay is still going to be negative. However, now y prime is going to be negative 2. So we get minus minus. That means that for any point in this region, we are decreasing in the x direction and decreasing in the y direction. And so our trajectory is going to be decreasing in both. Okay. What about in region 3? Right, we're going to get x prime greater than 0, exactly. Y prime less than 0, exactly. And so the little symbol here is positive, negative. So we're increasing the x direction, decreasing in the y direction. And we get that. Again, this is just a little rough sketch. And then what about region 4? Plus, plus, exactly. Increasing in both x and y. And what we see is exactly what we expected, actually, right? We see that around this, this equilibrium point, we have a kind of spiraling behavior. So, I mean, we know what the solution here is, right? We know that the solution here is actually closed curves. And it's important to note that we can't actually see, so this trajectory picture could be the same for, you know, some sort of expanding spiral, for, you know, a contracting spiral, or for closed curves, right? We get the same trajectory picture. But the point here is more to figure out like what the rough behavior is, in fact. And certainly, you can see that if we had a sink, if we had a contracting node, then all of the arrows would be pointing inwards. And if we had an expanding node, then all of the arrows would be pointing outwards. So we can get some sort of rough behavior from these trajectory diagrams. Of course, anything more precise, we have to do a little more work. But it's a really good sort of first pass in understanding the behavior of these things. And we'll see later in the lecture that you can use these diagrams to understand quite complicated parameter space behavior. Okay, so are there any questions? So this is like the basic analysis, and we'll do a bunch of examples of this, that anytime you write down a system of autonomous differential equations, a system of first order autonomous differential equations, you should always just do this analysis. You should always draw a trajectory diagram, figure out where your equilibriums are, figure out where your null clines are, and just get some sort of rough idea of what the structure of the solution space is. You can, of course, explore this numerically as well, and there's tons of great tools to do that. So some of you, of course, have already started doing slope plots, but that's what we're going to do in the third lab, is looking at slope plots. But numerical solutions are always going to be a little bit imprecise, and sometimes you can get the two of them together are really where you can get the best view of the possible space. There's also something to note here, right? That basically what we're seeing as we move around from region 1 to region 2 to region 3 to region 4, every time we cross a null line, the sign of one of these two variables changes. And this is actually like by definition, right? Because these null clines are where one of the derivatives is 0. So if we're going to cross from, if for instance, x is going to change from positive to negative, yeah, so if y is going to change from positive to negative, or x is going to change from positive to negative, then we have to cross a null cline. Okay, so if sign changes for x or y, must cross a null cline. And sorry, I apologize, because I mislabeled these. Because y is equal to 0 is the x null cline. And this is the y null cline. And so even more so, when we cross the y null cline, we can see that the sign of the derivative for y changes. Crossing, say, I shouldn't say the, because we'll see that there's many, a y prime equals 0 null cline often changes sign Okay, quick question. Why do I say often? I'm using some kind of hedging language here. What would be the situation in which we had a null Klein, right? So y prime is equal to 0, but we don't actually change sign as we cross it. The sign of y remains, say, positive or negative. What kind of situation could that possibly be? Or what would be an equation that where such a thing happened? Well, one example, to decide, note. When you have higher order zeros, a null Klein might not change the sign of the derivative. So as an example, if we had x prime equals, say, minus y squared, y prime equals x squared, the sign of the derivative is going to be constant. Sorry, the sign of the derivative is always going to be non-negative. Sorry. Less than or equal 0 for all xy. So this is our typical quadratic case, right? The sign of derivatives doesn't change if we have a quadratic 0. Okay, any question? Okay, so look at another example. So let's return to the SIR model. So as you guys are now sort of well familiar with, the SIR model is S prime equals minus beta Si, I prime equals beta Si minus gamma I. I'm going to just drop the R for the moment, since the R kind of is where everything pools up anyway. And this analysis is a lot easier to do when you only have two equations. You can certainly do it with more, but it becomes a little more complicated. Okay. Let's draw a trajectory diagram. So first, the equilibrium solutions are trivial. It's just, well, okay, we have an equilibrium solution, or sorry, they're not completely trivial. So equilibrium solutions are going to be I equals 0 and S equals S naught. And the other one is going to be I think that's actually it in this case, because, yeah, that's actually it in this case, because, of course, the other, we also have, okay, that's the equilibrium solution. The null clines. So this is a little bit more interesting. So we have I prime equals 0 null clines. We've got two solutions. So one is I equals 0, and the other one is S equals gamma or beta. And for S, we have, well, we've got I equals 0 again, and we have S equals 0. Okay, so let's then draw our trajectory diagram. So in this case, of course, I only care about the positive part, so we're just going to stick there. So here we have S and I. We've got our two null clines. So we've got multiple null clines now. Actually, we've got 3. So we have I equals 0. So this is a, I equals 0. And RS prime equals 0. And then we've got another I equals 0 null cline right here. So this is at S equals gamma over beta. And so let's draw the trajectory diagram out really fast. So we've got two regions. So again, we're going to look at the regions between the null clines. So one region is going to be when S is less than gamma over beta. And what is the behavior when S is less than gamma over beta? So we have our X prime and Y prime. And are they going to be greater than or less than 0 when S is less than gamma over beta? Of course, our other region is going to be S being greater than gamma over beta. Right, so we're going to have decreasing, decreasing. And so this is X, sorry. S is decreasing, I is decreasing. And what about on the other side? Exactly, decreasing, increasing. Okay, so this is actually an exact visual representation of the critical town size in some sense. Because basically what this is saying is if S is on one side of this line, then we have an outbreak. And if S is on the other side of this line, then we don't. So what we're seeing here this is a nice picture. So, and again, of course, we sort of know what these dynamics are because we've been playing around with the models, but we can really see, what this is supposed to look like. And we can also see something which maybe wasn't quite as apparent in the other models, which is that the closer we are to the critical town size, the smaller the outbreak will actually be. It's clear here. Closer gamma over beta S naught is, well, I shouldn't say it was what better. The fewer total people will get sick. This is, of course, in parentheses, given a fixed number of initial infected. And so, of course, the way to read this is we would say, so if we have basically sort of one initial infected, then we're looking at these curves here. Of course, if we have 100 initial infected, then we would be starting at this curve here, and we may get a lot of people sick. But it's kind of a nice thing because, that piece of information, it sort of intellectually makes sense and it seems relatively obvious, but it's very, very clear from the trajectory diagram in a way that maybe it's not as clear if we are playing around with lots of different kinds of solutions numerically, or even trying to solve this thing out a little bit more explicitly. And you can also see that, okay, so of course, we've actually gone and simulated this, so we know that these are what the solutions look like. But they can't really look that much different, right? I mean, we know that, S is always decreasing and I is always increasing until we hit the critical town size, at which point the number of infected starts decreasing until eventually we hit one of our equilibrium solutions here. And the whole thing, I mean, of course, secretly we don't ever hit it, we're just going to get exponentially close. But until we basically hit one of our equilibrium solutions here and everything stops. Okay. So are there any questions? On this graph, y is s prime equals 0. Yeah, so that's so s prime equals 0. The reason, yes, that's a very good question, and this is going to get more confusing. So I'm glad that you brought it up. So right, so s prime equals 0. Might actually start drawing the null clines in a different direction, but there's two null clines for s prime equals 0, right? So one is I equals 0, which is going to be the s-axis, but the other one is s equals 0, which is the I-axis. And this will maybe be a little bit more clear in the next example where we have some null lines that aren't actually straight. But the curves of the null lines themselves can be anything. They don't necessarily have to, they can be any curve in I and S. But the reason that I have S prime equals 0 labeled here is because the I-axis is when S equals 0 is given by the S prime null line, is given by setting the equation for S prime equal to 0. But we'll revisit this a couple of times because that's an important question, and we'll see a less trivial example of it here in just a second. Yeah, I think this is yeah, we'll see a less trivial example. Hopefully it'll become a little bit clearer because this is definitely a case where it's almost too trivial to see what's going on. Any other questions? Okay. Let's add in SIR modified. Okay. So once we have this basic model and we really understand it, and I think we're approaching saturation with how much we can get out of just the pure SIR model. Of course, one of the games that you want to play is trying to add in more factors that simulate things that may complicate the model in important ways. So as a first example, well, I shouldn't even say a first example because we've already seen several in the homework. But let's just consider the idea that we just have a flat number of people entering the system. So SIR with incoming population. So here we're just going to have S prime is equal to, well, we're still going to have our people getting sick, but now we're just going to add a flat incoming population D. And I prime equals SI minus gamma I. Okay, so let's do our quick analysis. Oops. For solutions-based analysis, and I encourage you to do it with me. So first, I'm actually going to sort of reverse the order now. So let's first find the null lines. So the null lines are going to be when S prime equals 0, and I'm actually going to make these purple. So the S prime equals 0 null line is just going to be D equals beta SI. Okay, it's a curve, right? I can solve this as a function for I in terms of S or S in terms of I. It's a perfectly fine curve. And then I equals 0. Well, we're going to have our standard two null lines that we've had before. So I equals 0 is one solution, and our other solution is going to be gamma over beta. Okay, so now our equilibrium solutions. Okay, so now here's the thing to observe. The equilibrium solutions are always going to occur at the intersections of two null clines, but specifically, they're always going to occur at the intersections of null clines from different from different equations. So I'm just going to state that. So equilibrium solutions always occur at the intersection of the null clines from different equations. I should actually say from n different equations. So here, that means that we have two equilibrium solutions. So I equals 0, plugging it into this equation here. So we're going to have SI equals 0, 0 is an equilibrium solution. S equals gamma over beta. And then I equals D over gamma is an equilibrium solution. But the intersection of the null clines that just corresponds to I. So I S equals gamma over beta, I equals 0 is not solution. Right. And looking at these equations, like that's kind of straightforward, right? Because, well, gamma over beta doesn't set S equal to 0. So gamma over beta 0 doesn't set S equal to 0. Okay, so fine. But it's important that like what that's really saying, right, is that if we want to use the null clines to find equilibrium solutions, we can take the intersections, but we have to take, we have to take the intersection of one null cline from one equation, one null cline from another equation, one null cline from another equation, et cetera, for a full complement of n different equations. Any questions about that? Okay, well, let's draw the picture. We've got S, we've got I. So let's draw on our null clines. So I'm just going to sort of draw this as a rough sketch, right? So beta and D or something. I'm not going to be too precise, but positive real numbers. So that means, of course, that that this line here, it's basically going to look like 1 over x, right? I equals 1 over s. So beta si. And then we have our two null clines for I prime. So one is I is equal to 0. And the other one is S equals gamma over beta. Oh, I'm sorry. I just wrote this down as an equilibrium. Sorry, I apologize. This is not an equilibrium solution at all. I'm clearly not on my game today. I apologize. So if this is an equilibrium solution, this is not an equilibrium solution. Okay. And here we can see it exactly, right? So we have one equilibrium solution. Add gamma over beta, d over gamma. All right. So now we've got 4 regions. Lightly mark them. 1, 2, 3, 4. And let's figure out the trajectories in each of them. Rough trajectories. So in region 1, okay, so in region 1, let's remind yourselves, sorry, I'm just gonna rewrite the equations down here. So we've got s prime equals minus beta is plus d, and we've got I prime beta is minus gamma I. Okay, so we have to think a little bit maybe about how to estimate these guys carefully. And we can, of course, be like a little bit more or less precise. But the way that I feel is easiest is to think about this in terms of asymptotic limits. So a very straightforward way to figure out these trajectories is to pick a region where we can kind of just think like, well, okay, so asymptotically, what does this look like? So as an example, well, let's just say, well, okay, let's say region 1, right? So in region 1, let's assume that both S and I are very, very large. So assume S and I are very large. Then what is the sign of S going to be and what's the sign of I going to be? Well, okay, so the sign of S is going to be, so if we have S and I and they're both very large, then S times I is going to be very large. D is a constant. So we're going to have minus something large plus a constant. Okay, eventually it's going to be negative, right? A negative thing that we can make arbitrarily large plus a finite constant is eventually going to be negative. So similarly, in terms of I, if we have, say that S is about the size of I, so if we have S and I both very, very large and about, how can both be large at the same time? Okay, right. So I'm not, good question. Yeah, so I'm thinking not not on this line, but in this region, right? Where this region, and let me just, I just stated, so this region is the set of points. So basically this is where S is larger than gamma over beta, and I is larger than, sorry, D over beta S. Right, so it's basically everything from here off to infinity. So that's why I can decide that I can take, yeah, good question, though, thank you. Yeah, that's why I can decide to take I as big as I want. I mean, we can also just enforce these conditions, right? So putting this into these equations, we can just ask, so if I is greater than, and yeah, so let me give you the, I'll give you the heuristic way, and then I'll do it like a little bit more precisely. Right, so if we assume that S is approximately I is much larger than 1, then basically, then beta IS is going to be much larger than D, so S prime is going to be less than 0. Similarly, beta IS is going to be much larger gamma I, so I prime is going to be greater than 0. So we get minus plus. More carefully, if we have S greater than gamma over beta, and I greater than D over beta times S, then we can actually try to work these out within these equations, right? So then S prime, we want to work this out. So then plugging this into equation 1, we're going to get that minus beta IS plus D. So if I is larger than this, then this is going to be less than minus beta when it's equal. Well, okay, that's 0. Yeah, sorry. So yeah, this is, yeah, sorry. In the interest of, yeah, but basically, you know, the carefully working out is just, so this of course is just going to be forcing this quantity to be large, whereas this is going to be forcing, so this is of course I times beta S minus gamma forces this quantity to be large. And so you can see it directly from the equations. Okay, so given that, there's kind of two ways that you can go around the circle and figure it out. So you can do a similar kind of asymptotic analysis, but we can also use the fact that we know that there are no higher order zeros in this equation, right? These are both, all of these nullclines are first order. And so when we cross a first order nullcline, that means that we have to change sign, right? So in particular, when we cross one of the I nullclines, we have to change the sign of I. And when we cross one of the S nullclines, we have to change the sign of S. So we can go around in a circle. Just write that down. Nullclines are first order. So crossing any one will change the respective sign. So in particular, we have the I null lines in green and the S null lines in pink. So if we go from here, so this is going to be what? Decreasing in S, increasing in I. As we cross this null line, what do? Well, we change the sign of I. So now we're doing this. Then as we cross the pink null line, so change the sign of I to minus. Minus, as we cross the pink null line, we change the sign of S. And as we cross the green null line again, we change the sign of I. All right, so any questions? Okay, so again, this doesn't give us like a ton. So this gives us a lot of information, but we have to be a little bit careful with it, right? So this picture that we're seeing here, this could be a sink, right? So this could be something like that, where all trajectories, you know, are kind of falling in to this thing. It could also not be, right? It could also be a spiral, something like that. And it could also be, oh, how do we confidently say that solutions are spirals instead of nodes? So that is a good question. And so the way that we do that is we actually solve for the equilibrium solution. Yeah. I would say before we jump on, and so that is exactly the next thing we're going to do. So it does still low, so it doesn't tell us, yeah, so it doesn't, this picture doesn't tell us whether this is a spiral or a node, or, I mean, in fact, this could like be an increasing spiral in theory, right? This could be, that's pretty consistent. We can't cross, we can't, or we have to be careful when we cross null lines, right? So, and in fact, if you see this, let me actually extend this just a little bit, because we could, of course, think about the regions below that are outside the model domain. And what we would see pretty fast, right, is so if we cross this this lower null line here, this is going to be an I null line. So crossing it actually, oops, going below, we would change the sign in I. So this is we're sort of being forced upwards here. So if we could cross this null line, some weird stuff would happen. But this null line is also where s equals 0, and so yeah, we'll work to cross it. But yeah, so then how do we say, okay, so here we are. How do we say firmly and confidently what is actually going on? Yeah. Oh, I would actually say as well, we can't cross this null line because if we were to come down and hit it, this is kind of an interesting thing to know, right? When we hit this null line, I has to be equal to 0, or so I prime has to be equal to 0, which means that because of the uniqueness of solutions for autonomous differential equations, we're actually kind of stuck there. I'll turn that. What is the actual behavior at the equilibrium solution? So this is what is called Jacobian analysis. So we want a higher complexity analog of our nice equation that we were able to completely classify x prime equals a x. So, okay, so the obvious higher order choice. So for nonlinear, systems, so let's write, say, x1 equals, sorry, x1 prime equals f of x vector, right? So we just have, so x1 prime is some function of the others down to xn prime is, sorry, f1, fn x. We can package all of this into one function. So x prime is equal to, we'll call this capital F of x vector, where f is equal to f1 up to fn. Okay. So what we want to say then is, so suppose that we're close to an equilibrium solution. Suppose a solution x of t is close to an equilibrium solution. We'll call that equilibrium solution x sub e. So it doesn't have to be close for all time, just for some small interval. So for t in some, for t in some small interval. So basically what we want to talk about here is the local behavior. Of course, it's going to turn out that we really can't say anything globally, or that there's some things we can say globally, but not very many. But we can think about, like, so what if we're just close to an equilibrium solution? And so then the idea is to Taylor expand. Taylor expand at E. Okay, so what does that look like? Well, we have now f prime at E is going to be, and so when I'm saying Taylor expand at E, we can use the multivariable Taylor formula, but really I'm just using the single variable Taylor, or sorry, just using the sort of chain rule version of the Taylor formula for each of these, for each of the equations, right? So you can say it. So kind of what we're doing is we're going to say, so for each equation, we're going to write f1 at x at plus e plus, and then we write out the whole Taylor formula. So the higher order derivatives, so sum of del f1 del xi times x I minus x e sub I equals 1 to n plus, etc. Xn is going to be equal to, same thing, but n So we can compactly summarize this in the multivariable Taylor expansion. So write this as x equals f of xe plus df dx bar at, dx vector at e times x e plus higher order terms, say higher order. And this is going to be where this this term df dx bar is what's known as the Jacobian. So it is the matrix of partial derivatives. So it is going to be df. df1 dx1 df2 dx2 up to dfn dxn down to df1 dxn. Oh, sorry. My indexing wrong. 1 1 and 1 2 then dxn. And so this is what's known as, be consistent in what I'm writing down. Okay, so quickly, are there any questions about this setup so far? Okay, so now what does this allow us to do? Well, of course, we sort of know what we want to do, right? This is going to be our standard Taylor approximation game. These higher order terms, we're going to say that we're close enough to the equilibrium solution so that they vanish. Since x is an equilibrium solution, f is going to vanish. And what that means is that we're going to be basically left with something linear. So now we have that f x sub e is equal to 0 since x is an equilibrium solution. So setting delta x equals the difference between x and the equilibrium solution. We can write we're going to have that delta x prime is equal to, well, okay, the equilibrium solution is constant, so we take the derivative with respect to time, and we just get constant. So it is x bar prime, and that is going to be not equal to, but approximately f of x e plus df dx x equals e times the difference between x and the equilibrium solution plus some higher order terms. So what happens? This goes to 0. This is going to be delta x. This is a constant matrix. And so we are left with the equation del x prime is approximated by the Jacobian at xe of delta x. And then this is the Jacobian at x. Okay, so great. So this is a first order linear equation. And what that means is that we can analyze the behavior using the eigenvalues. Approximate. And eigenvectors. Okay, so I'll go through and I'll do a sample calculation in just a second here. But are there any questions before I do that? Basically, this is our old, any of you are coming from a physics background, this is your standard old physics trick. If we say, well, when we can't solve something, let's just linearize and at least get a solution close to the equilibrium points. Okay, so returning to our example, what did we have? So we had this SIR with death, sorry, with an incoming population. So we had S prime equals beta Si plus D. We had I prime equals, beta Si minus gamma I. And so what this means, right, is that our F of, well, I'll just write it as F, it's F of Si is a two-component function. One component is minus B S I plus D, and the other component is, beta Si minus gamma I. So we just need to compute the Jacobian. J at Si is equal to, again, it's the partial derivatives. Since I don't have a unified vector for S and I, I'm just not going to bother writing that, but this is going to be F1, dF1, ds. I'm going to read the index incorrect. Yeah. dF1, di, dF2, ds, dF2, di. takes on a relatively straightforward form. So the derivative of the first function with respect to s is just going to be minus beta I. D is constant, so goes away. Derivative with respect to I is going to be minus beta s. The derivative of the second function with respect to s is going to be beta I, and the derivative with respect to I of the second function is beta s minus gamma. Okay, any questions? All right, so now at the equilibrium point, the equilibrium, we recall, is going to be at S is gamma over beta, I is D over gamma. Gamma over beta, I is D over gamma. Then, so plugging in, we have J E under them is going to be, so plugging in EI, we're going to get minus, oops, beta D over gamma, and then minus gamma, beta D over gamma, and then plugging in for S, we get 0. Great. So now, to increase our layers of complexity, now we just go back and we do what we did last week. We want to find the, so we want to classify solutions. And what that means is we want to understand the eigenvalues. And so we can either do this using the trace determinant plane, or we can just do this using by just deriving the eigenvalues, right? But we know that that the I'm just going to write it out just in terms of the eigenvalues. So the determinant of J minus lambda I is going to be minus lambda times minus beta D over gamma minus lambda plus beta D. Okay. Factor out lambda squared plus beta D over gamma lambda plus beta D. So lambda equals minus beta D over gamma plus or minus the square root of beta D over gamma squared minus 4 times beta D over 2. And so there's two relevant things that we see from this. So first, is this going to be a stable or unstable focus node, whatever it happens to be? Yeah, it's going to be at least stable or semi-stable. It can't be unstable first, since minus beta D over 2 gamma is less than 0, must be at least partially stable. should say at least semi-stable. We also now have a condition for whether or not this guy is going to be for whether or not this is a focus or a node. And that condition is exactly that delta equals beta d over gamma squared minus 4 beta d is greater than 0. Well, it's possible that it's semi-stable. That we can't at the moment rule out that for some parameter values this could become positive, right? So if delta here is positive, so this is real, it's possible that we could add something onto this. Although I guess you're actually right, because as long as, well, is that true? Yeah, I think it's possible. Okay, so we're forcing this to be positive. No, I think you're actually right. Yeah, so I was being a little bit careful, but we can go farther. Yeah, we can say that this is stable because this term is always, since we're restricting beta and d to be greater than 0, this term is always going to be less than this term in absolute value. Yeah, that's good. Yeah, it's a good observation. Okay. So this, though, gives us a nice criteria. So this gives, so in this case, we're going to have a node. So we have an exact criteria. Exact classification of the behavior. Of the local behavior. In particular, if BD is greater than 4 gamma, we have a node. Beta D is less than 4 gamma. We have a focus. Yeah. It's possible that right, so if delta is greater than 0, we have a stable node. If delta is equal to 0, then we have a stable inflected node, which means in this case that yeah, which locally, since it's a local behavior, actually is kind of we're going to see is it's a little, yeah, it's inflected, but it's kind of it looks stable essentially. Yeah, definitely. Yeah. And then right, when delta is less than 0, we're going to have stable. We're going to have a stable spiral. But you could see it's possible. So in this case, it doesn't happen. But it's possible that delta could actually be larger than BD over gamma, right? And if delta was larger than BD over gamma, then we would have a semi-stable situation. It's the fact that that this term here is in terms of the beta and the delta that forces this to always be smaller than this term here. But generically, I mean, in most cases, if you hand me a polynomial, it's entirely possible that this term will be larger than the absolute value of this term, in which case you'll get some positive solution and some negative solution. Then you'll have a semi-stable solution. Okay. So any questions? We'll take a break in just a second, but first I want to just show you this actually in action. So The fact that we have an exact formula for this is, yes, I do. The fact that we have an exact formula for this is great, but it's not, yeah, so the fact that we have an exact formula for this is great. But we can actually, so we can just go through and we can look at the numerical solutions, right? So in particular, if we need gamma times beta to be greater than, beta times delta to be greater than 4 gamma, let's just look at what we get. So here's one of these cases. Okay. And this is exactly what we expect. So here I've drawn on the null clines, and I've started at a couple of different starting conditions. And we see that we get this this stable node. And we can kind of look at what happens as we go down through the, we can look at what happens here as we go down through the, as we let beta pass down through the threshold where, so here, since I have gamma equals 1 and d equals 1, our condition is that beta is greater than 4. So as we go down, we have beta 4, beta 5. Okay, so we're getting some sort of maybe-ish spiraling behavior, but things are still falling into that point pretty fast. At beta equals 4, this is where we get the inflection that Sai was pointing out. And then let's drop below to beta equals 3. And you can start to see the beginnings of some spiraling behavior around there. Let's drop far below to beta equals 1. Okay, so here we have like some actual, you can really see the spiraling behavior come out. And the picture here, of course, right, is that if we zoom way in, so here I've just done that. So if we just zoom way in, then this null cline linearizes, right? This null cline's already linear, but the whole thing basically linearizes, and we're basically in the case of the linear functions, and we get this spiraling behavior in. And of course, the interesting case is the inflection point that Sai brought up. And here's what we get at that point, that double zero. So you can at least see visually that there's, this is the point where we cross from having sort of small spirals, right? 3.8. And again, we may have to zoom farther and farther and farther and farther in to actually see the spiraling behavior, but that is sort of the point where we cross from having a sink to having small spirals. And here where we have the sort of obvious sink. Okay. So one of the takeaways, thank you. I'll post this code if anyone wants to take a quick look at it. But I mean, it's one of the things that I find, so I mean, I'm somebody that I love like doing mathematics by drawing pictures. I love it when you can draw these trajectory diagrams and do some like substantive mathematics. But it's important, if we remember we had the trajectory diagram is exactly the same for this case as it is for this case. The only thing that has changed, and if you'll notice actually as well, if you look at these graphs, in some sense, really the only thing that's changing, and I can even make it more precise. So here, let's do 10. And if I just change gamma, right, then the only thing that's going to be changing is that I'm going to be moving the null cline. Of course, I should actually say where the null cline is correctly located, right? So I'm just going to be moving that vertical null cline. So if we put gamma to 10 as well, oh, that's way too far. Put gamma to 2. We start to see the spiraling behavior. We put gamma to 4. And we definitely see the spiraling behavior, right? And all that's happening is I'm pulling that null cline from the left to the right. I'm pulling that vertical null line. Everything else is staying fixed. And so there's some very deep way in which like all of the geometry that goes on in these solutions is dependent entirely on these null lines and on the movement around them. And if you can kind of understand how the movement of these things affects the behavior, you can really understand what's going on with these differential equations and really control them, right? You can start actually creating differential equations based on the kind of behavior you'd like by specifying certain kinds of null lines and certain kinds of roots at them. But yeah, it's a really, it's a cool industry, and we'll be playing around with this in the lab and the homework for this week, and in a slightly more complicated example. But in a slightly more complicated example, we're also going to be overlaying the slope plots on top of these things. Okay, so it is 2:41 my time. Let's take a 10-minute break, and we'll be back at it's 2:42, so we'll be back at 2:52 my time. And we'll take a break. I'll try to go ahead and actually just post this to Colab while we're on break here really fast, so that if anyone wants to mess around with it, they can. Let's see, be in the. Yes, I have the joy of being out of quarantine again, so I have stable internet, which is amazing. And of course, if there's any questions, feel free to ask them while I'm messing around here. Okay, there's something weird going on. So if anyone wants to take a look at this, that should give you a working collab link. And yeah, I'm going to run and grab more coffee. I'll be back in about 3 minutes. Okay. All right, so are there any questions before we get started? Jump back into the equations. We'll be sort of jumping back and forth a little bit between equations and simulations today. So, well, okay, and for the rest of the class. All right, so we've been looking roughly so far at various kinds of population and rate models. And there's another population model, and we're going to sort of start to combine these things. And we're going to even on Wednesday start to combine them with spatial models. We'll start talking about spatial models. And then one of the last steps in this class is going to be to sort of put everything together and think about population spatial modeling. But one of the most important sets of population models that we have is the predator-prey model. So this is the Lotka-Volterra equations. Equations. And so here's the idea. So the Lotka-Volterra equations are basically to sort of ecological modeling as the SIR model is to epidemiology. It's like the most basic thing. It's actually quite powerful. And it turns out you can really read a lot of interesting behavior off of it by just making some very minimal changes to it. Okay, what are our assumptions here? Let's assume that we have two populations, a population of predators and a population of prey. Let's call predators Y. So we're going to assume the populations are long enough, sorry, are large enough that we're not really being concerned about individuals. That the predators themselves, so that we can think of them as a continuous mass. Well, yeah, predators and prey. We want to assume that if there weren't any predators, just as a very basic, simple assumption, that the prey would increase exponentially. Without predators, prey would increase as x prime equals birth rate minus death rate times x, or exponentially. Well, yeah. So the birth rate minus the death rate, but ax exponentially. So similarly, we want to assume that without the prey, the predators would die off. And that they die off exponentially. So basically the assumption here is something like in order to birth offspring, they need to hunt. So we have a birth and death rate. Without the death rate, so the death rate for the prey relies entirely on the predators. whereas the death rate, and maybe some token death by old age, but in general the birth rate is much larger than the death rate. Whereas for the predators, that's not true. The death rate is much larger than the birth rate without a sustainable source of food. So y prime equals minus by. So say birth rate is higher than death rate. Death rate, whereas for the predators, without prey, the death rate is greater than the birth rate. Okay, so we've got ourselves a birth rate, we've got ourselves a death rate, and we just now need to specify the interaction. So predation. And we're going to use our sort of normal, how do we think about predation? Well, we'll say that there's some probability that a member of population A meets a member of population B, and that member of population A successfully hunts the member, so one population successfully hunts the other. And that's going to give us essentially well, it's going to give us an interaction term. So predation, some percent chance any predator percent chance, we'll call it P, for any predator to meet any prey. This is, of course, I mean, we're making some big assumptions here. This is some sort of well-mixed environment. But it might be helpful, instead of thinking of like lions and tigers, to think of, locusts and, and sparrows or something like that. Something where you could really assume that there's some kind of mixing. I guess I shouldn't say lions and tigers since they're not predator, lions and antelopes. There's some percent chance that for any predator to meet any prey, there's some percent chance that the hunt is successful. Percent chance H, hunt is successful. And that has some impact on the population. And that increases predator birth rate by some amount. Some R. So then we have the change in X due to predation. Well, I'm actually say it this way. So that is going to then yield the following. So we have roughly X prime is going to be, well, we have some background growth rate, and then we have some chance that any member of the population meets another, so any prey member meets a predator, times some chance that they are successfully hunted, times then the number of prey times the number of predators. And we're just going to pull these variables in. Oops, and call this minus C1 XY. And similarly, y prime, we have the increase in the population is going to be given by whatever the effect that successfully hunting has on the rate. So rate times the probability of successfully meeting and successfully hunting times xy minus b, so the background mortality. And we're going to call this, we're just going to call all this C2. xy minus by. There's some relation between C1 and C2, but it's going to make things easier to derive if we just relabel them. Okay, so are there any questions? Okay. So here we go. So let's go through our process now. So whenever somebody hands you a new set of equations, you should write down some null clines, you should find some equilibria, you should draw the trajectory diagram, and then the next step is going to be, we should classify the equilibria. So and these should be really the steps that you follow. Because again, and I'll talk about this a little bit more on Wednesday, but you should start thinking a little bit about what you want to do your final project on. And definitely, viable final projects are taking the kinds of situations that we've been thinking about modeling. That's a good question. Yeah, so that's a good question, Sai. So we can think about logistic growth. Basically, it's because this model is slightly simpler. But the kind of one of the immediate next things to do is to crowbar logistic growth in, or not crowbar, include logistic growth. And what we find is that the dynamics are reasonably different. But yeah, so that's exactly, so I mean, and I mean, on the final project, that's, I mean, the kinds of questions that are great to explore. So if you wanted to take one of these models and do something like add in logistic growth, yeah, exactly. So I mean, I would say that you would need to do something a little bit more complicated because that's actually in the book. So that's pretty well understood. But something like that, taking like an SIR model and throwing in logistic growth, or we'll see some of the extensions of these models, and there's some nice things that happen. Yeah, but that's how you want to be thinking for the final project. Okay. Sorry, null clines is one word now, it's one to be two. Okay, so what are the null clines? So we're going to have some x prime null clines, and we're going to have some y prime null clines. So first, what are the x prime null clines? You're correct. You need to say a little bit more about what exactly is each of those things. Exactly, right? So we're going to have y equals a over c1 and x equals 0. And what about the y prime null clines? And what is, yes, yeah. So we're going to have then y equals 0 and x equals, x equals b over c2. So now we actually have 4 null climbs, right? And so what are the equilibrium solutions going to be? So the sort of computation here is to think back to, you know, where else we've done multivariable algebra, which is like in Calc 3 when we're doing optimization problems. There's going to be 2 equilibrium solutions. What are they going to be? Yes, that's correct. 0, 0 is going to be one of them. That's good. If 0, 0 was an equilibrium solution, we should be very suspicious of our equations, at least in a population model case. What about the other one? That's correct, right? So it's going to be our b over c2, a over c1. So y is, and y, let's make sure, is, oh, let's say 0 a over c1 not an equilibrium solution. What do you think? Any guesses? Does anyone remember? I mentioned it before. And this is a really common point of confusion. So don't, if you don't immediately see it, it's all right. Exactly. So y prime is not equal to 0, right? So basically, we have 2 conditions. So the equilibrium is 2 conditions. X prime is equal to 0 and y prime is equal to 0. If we take an equation from one and the other, then we guarantee that both these conditions hold, right? But if we find the intersection of just 2 equations from the same condition, okay, well, in this case, you know, x prime would definitely be 0. It would be very 0, but it doesn't tell us anything about y prime. And you can just plug it in up here to check as well, right? When x prime is equal to 0, then, you know, and sorry, when x prime is equal to 0 and y prime is ac, this is definitely not going to be 0. So an equilibrium solution. Because y prime is not equal to 0. Okay, any questions about that? Okay, So let's draw the diagram. We don't care about negative populations, so prey and we have our predators, and let's include, so our x null clines are going to be that y equals a over c, and x equals 0. So here is exactly that, that intersection that is not actually an equilibrium. Similarly here, we have y equals 0 and x equals b over c2. All right, we've got 4 regions. We just need to do the trajectory diagram. I should say, of course, we have our equilibrium, or equilibria here and here. So this is our b over c2, a over c1, 0, 0. While I'm drawing this picture, I challenge you to figure out the slope diagrams yourself. We've always had 4 so far, but there's actually no reason why you need to have 4. Why you need to have 4 regions. It's just any regions between the intersection of the null clines. So we have rough trajectories. Region 1, regions 2, 3, and 4. And let me write the equations down here again. So x prime equals ax minus c1 xy, and y prime equals c2 xy minus by. Great. And so quickly when we think, so we can look asymptotically, pick a region. So for instance, in region 1, what do we expect the trajectories to be? And again, you can kind of think about it, okay, so what are the exact inequality relations? Or you can just think about, you know, what is the asymptotic behavior? What do we think? So in region 1, what will the trajectories be doing? Minus plus, yeah. And so the way that I would kind of think about that, right, is again, if we have x and y being roughly the same, yeah. So if we've got x and y being roughly the same size and very, very large, then x times y is going to absolutely dwarf the x term. The quadratic term will dwarf the linear term in both cases. And so we'll get minus plus. And then, so decreasing in the x direction, increasing in the y direction. And then we cross the y null line. That's going to flip. Cross the x null line. That's going to flip. Again, since all the behavior here is first order. So all of these zeros are first order zeros. And flip. So minus, plus, minus, plus. Are there any questions about that? So quick question. We sort of don't know what this zero's behavior is, right? But there actually is kind of something that we can say about this 0. what is the stability type, or what is the actually what is the, we should yeah. Yeah. We can actually say quite a bit. Yeah. What is and one way we can say it is if we want to allow ourselves to jump over and think about these. So if we cross this null line again, x is going to be like that. If we cross this null line, y is going to be like that. So what is the stability type? Stability type 0, 0. What would you guess? I mean, and I would say, you know, as we saw a second ago, we have to be like a little bit careful with these things, but we can make actually a pretty good guess for 0, 0. Well, it's not going to quite be stable, right? Because we see things moving away from it. And in fact, you know, we can actually sort of draw what's going to happen on the null clines as well, right? So on the null cline, we can think if so if y was actually 0, right? Then looking at this equation, if y was actually 0, then x would just be positive. And so along the null cline, we're going to have this. And similarly, if x is 0, then then x prime is 0 and y is negative. And so we have this. And what does that indicate we're going to get? Semi-stable, exactly. We can almost read it off from there. Kind of expecting orbits that do that. So I'll say semi-stable, and I'll put a question mark in there, right? Because we do want to be a little bit careful. You know, I've certainly given a pretty convincing argument, but you know, it is far from a mathematical proof. But this diagram anyway, though, it gives us a pretty good idea what's going on. And if this is in fact semi-stable, that would sort of make intellectual sense, right? Like we think, you know, so if as the prey population falls, eventually it's going to fall so low that the predator population, yeah. So size saying, so okay, we can think like prey can grow or predator can eat more. Yeah. So what we're seeing here is right, the predator population, or kind of the interpretation that I give here, right? So if x is small and y is large, so you have a small prey population but a large predator population, then the predator population falls until it's below a certain threshold. And you know, and in fact, you can kind of see what would happen here, right? Oops. So the prey population falls as the predators eat it, but the predator population starts to fall as well as there isn't enough prey. And then eventually the predator population gets low enough that the prey can start to come back exponentially. Now, of course, in the real world, you eventually get down to where there's a discrete number of prey and the last one gets eaten and you're done. But here we can, you know, this is real numbers. And so we can have, you know, 0.1 of a prey. But then the prey experiences exponential growth quite merrily. And eventually the predators start coming back as well because there's enough prey. And the cycle continues to go around. And the question is, what are the solutions then? Are they spiraling into the center? Are they spiraling out of control and getting into wackier and wackier cycles? And so the next step is to kind of find out. I mean, out of curiosity, some of you actually might know what the answer is. But just take a quick poll. What do you think? I mean, there's really no way that you can know what the answer is given what we said so far. What do you think? Are we going to spiral in towards the central equilibrium, or are we going to fall into the central equilibrium, or are we going to spiral outwards? What's going to happen? Right. So in this case, let's just figure it out. So we need to find the Jacobian, and we need to compute the eigenvalues of the Jacobian. So the Jacobian in this case is going to be J of x, y, matrix of partial derivatives. So secretly, of course, so the Jacobian is going to be the matrix of partial derivatives. So first equation with respect to x is going to be a minus c1 y. With respect to y is going to be minus c1x. Then the derivative of the second equation with respect to x is going to be c2y minus the derivative of the second equation with respect to y, which is going to be, sorry, not minus, c2x minus b. So let's evaluate it at the trivial. I shouldn't actually say trivial because it's not trivial. But let's evaluate at the origin, at the equilibrium at the origin. What are we going to get? I get a 0, 0 minus b. So lambda 1 is equal to a. And actually, there's more that we can say here. So lambda 1 is equal to a. Lambda 2 is equal to minus b. It's semi-stable. We actually know the eigenvectors here, right? The eigenvectors are going to be 1, 0, and 0, 1. And we could actually draw our entire diagram. We're contracting along the predator axis, and we're expanding along the prey axis, and that's exactly what we saw up here, right? When we're close, right? We're saying nothing about global behavior here. As we can see, as we move away from it, and things become very, very different. But if we're very, very close to the origin, then we are decreasing, the number of predators is decreasing, and the number of prey is decreasing. Sorry, is increasing. Okay. Any questions? All right. So let's look at then the little bit more interesting equilibrium solution, although they're all interesting. B over C2, A over C1. And what are we going to get? So here we're going to have, so 0, so it's going to be A minus A, 0. And then we're going to have minus, minus B C1 over C2. And then we're going to have A C2 over C1, 0. And Okay, quickly. So this implies lambda squared is equal to, what we're going to get lambda squared plus AB equals 0, or lambda equals plus or minus square root of minus AB. So what does that mean? Well, it means our solutions are purely imaginary. Purely imaginary. And what did purely imaginary solutions mean for what did it mean to have purely imaginary solutions in the linear case? Concentric circles, exactly. So the stability type is that of concentric circles. Circles. Well, okay, so of course we shouldn't actually expect concentric circles because this is just some Taylor expansion, right? So it's in red because this is important. Note. That's not red. We shouldn't actually expect closed solutions. And the reason, right, is that because we're Taylor expanding around 0, we're never actually around the equilibrium, since this is an approximation. Is just a moment. So I apologize. My software just crashed over here. Can you guys still hear me? Okay. Good. Well, all right. So this just crashed. Okay, and thank God it saved and appears to have come back. So let's try sharing this out again and see if we can make this work. Just 1 second. I apologize. Yeah. No, thank God for that. No, and luckily it looks like I don't know exactly what happened. It just but the notes are there, so that should be fine. Okay, so let's share the screen. Try this again. Okay, good. Wonder this poor little tablet might be overheating. Okay. Okay, so anyway, we shouldn't expect this to be closed, to actually be closed, because stability, sorry, to get rid of the floating meeting controls. Okay, because of course, stability here is approximate. Stability is approximate. And orbits actually closing up is exact. So in this case, though, there's something kind of nice you can do. In this case, there's a trick. That we can see. I'm not going to take you the whole way through it, but I want to really show you this trick. But we can write dx dt dy dt through a change of variables. Sorry, let me do this the other way. So through a change of variables, I apologize for the construction in the background there. This is going to be dy dx. And that is going to be, well, c2xy minus by divided by ax minus c1 xy. And if you notice, we can actually, so this actually can get kind of split up. So there's kind of a nice trick here in that we can rewrite this as basically y times, so it's going to be y c2x minus b over x a minus c1y. And what that means is we can separate variables. So we can write this as a minus c2y over y dy equals c2x minus b over x dx. Okay, so now what you get out of this is not an actual function. It's not kind of what you'd like to get. But you do get a relation for the solutions. And that relation is going to be, what you wind up getting is basically y to the a, y to the a, x to the b, and let me be consistent here, equals c1y plus c2x plus k. And so from here, you can prove whether or not, so prove the following. In the case of the, or I should say not homework, but exercise, prove that for the predator-prey equations, solutions do actually close. Do actually close. And we can see that. So let's just take a second and go back to our simulations. And tape over our screen, go back to the simulation here, and what do we have? Well, for the predator-prey equations, this is actually what we get. And this is, so this is of course a numerical simulation, but it's kind of impressive. So not only is it incredibly stable, but it's stable enough that the numerical simulation itself basically appears to close. And you can prove that this holds analytically. Just one second, I'm gonna see if I can stop the sawing. Okay, so they're going to hopefully wait until class is done until they do any more routing. Okay, but so yeah, so we get this kind of beautiful result that in the case of the in the case of the Loeb-Coulter equations, the orbits actually close up, and we get these sort of interesting concentric cycles where the prey increase, and then the predators start to eat them and increase, and that calls the population of the prey. They eventually die off enough that the predators die off, and the cycle sort of goes again and again and again. So are there any questions? So okay. So it's an interesting model, the fact that this is this cyclically closes up. But of course, really what we want to do with it, and what we're going to talk a lot more about, we're going to show some other population models, in particular the competition model on Wednesday. But of course, what we really want to do with this stuff is we want to use it for something. And so one thing that we can use it for as an example is trying to evaluate, oh, can it show the parameter values once? Yeah, I've got the parameter values listed. The parameter values, sorry, just one second. So the parameter values, yeah, it's fine. But it's just a, it's just everything equals 1. Yeah. So C1 equals C2 equals A equals B equals 1. Yeah, and basically what happens in this case is as you change the parameter values a little bit, yeah, I recycled the code for this and didn't update the title. As you change the parameter values a little bit, oh no, it's totally fine. And then the shape of this thing changes, but really nothing else does. It just kind of squeezes or expands it a little bit. You know, you move that central equilibrium around, but you do it in a pretty predictable way. So these Loeb-Coulter equations are really stable. So let's use them for something. Yeah, if I'd had a little bit more time, I would have built this out, and it wasn't just like a quick demonstration. I would have built it out to actually have the null clients labeled and everything, like I did for the previous example. Yeah. Let's look at a quick example of DDT and pest control. So let's assume that we have some sort of pest, like a locust or a crop-eating pest as an example. So this is where this actually came in. Assume we have a crop-eating pest. Have a crop-eating pest. Pest. But that's preyed upon by something that we don't mind as much. We also have a predator keeping it in check. Keeping it somewhat in check. So what we want to do is we want to simulate the effect of spraying a chemical agent like DDT that might actually kill both the predator and the prey. So we want to simulate pest control by a chemical agent like DDT. Like DDT, which may affect both populations. And those of you who, you may have run into these examples before, those of you who know some of the history of this, and we'll find something quite interesting. So let's just assume that DDT kills a percentage of each population. DDT kills a percent of each population. So then what we want to do, so we modify equations as follows. Equations 2 dx dt equals, well, it's going to be our equations from before, ax minus c1 xy, but now we're going to kill some percentage off. And, oh, sorry, so percentage off. And so basically what this is just going to do is this is just going to shift the value of a little bit, right? So a minus p1 x minus c1 xy. dy dt is going to be, then we're going to have our c2xy minus by minus p2y equals c2 xy minus b minus p2y. Okay, so of course, like mathematically, stability, blah, 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 all we've done is we've changed a parameter by shifting it. These are independent parameters. I'm changing them by independent parameters. Like literally nothing has changed. So our equilibrium solutions now are going to be 0, 0. And our other equilibrium solution is going to be, well, it's going to be now a minus p1 over, oh, sorry, got this backwards. It's going to be b minus p2 over c2 over c2, A minus P1 over C1. Oh, thank you very much. That's very important. Yeah. Okay, so basically this should give us some information about what happens, and in particular about how the equilibrium populations are going to change as we use DDT. How does the equilibrium population well, I want to just observe that something kind of crazy happens. And I'll show you exactly what craziness happens. But what I'll show you in simulation just a second. But let's just assume that we don't kill off any of the predators at all. Let's assume that P2 is equal to 0. How does how does the equilibrium population for the prey change? So what happens? I have stopped the, so I've just killed off, so the DDT now is only killing prey. It is not killing the predators at all. And what happens to the equilibrium population? Well, this is the surprising answer, and this has actually been observed in nature, and it's been a bit of a problem. The answer is nothing. So that's quite unintuitive, right? So if P naught is equal to 0, then the new equilibrium is just B over C2. Yeah, you'd think that, but I mean, that would seem to like make the most intellectual sense, right? Okay, so here we go. We've got predation, and then we're gassing these things as well. What must happen? Well, it must go to 0, right? Like nothing else can happen. But what we find looking at the sort of modified Loeb-Volterra equations is that actually the population doesn't change. The median population, sorry, the equilibrium population doesn't change at all. And all that happens is that the equilibrium population for the predators goes down, right? So in fact, equilibrium population for predators goes down. So by using some sort of pesticide that actually just kills off the prey, basically what happens is it devastates the prey. Yeah, I mean, this is very non-trivial. I mean, it's very surprising. I'll show you the simulated example. You know, it's definitely it takes looking at it a few times to make sure that I didn't make some sort of mistakes. So I've definitely made a few. But yeah, but this is what happens. So basically, the population dies off, or the prey population dies off, and the result is that, you know, then the predators can't eat, and so we still are winding up in this circle. But to kind of show the picture, show the equations, we can play around with these for a second. So we can ignore my bad coding, but here you go. So this is a picture. So this is a picture of what happens to the predators, and so we can see that as we move. So all I've done here is in the predator equations, I just shift. So in this case, I've shifted them both by a little bit. Actually, we can even take this shift off. And oh, I should take multiple places this way. So we take this shift off, or sorry. And what we get in the case, so the more interesting case here that we want to see is the prey equations, right? And here, what we see is that it's completely stable. So here I'll put a smaller number. So we just are going to shift by 0.1. Okay, and we see that we have lower peaks, but we also have lower sort of troughs. So basically, the predators, since they sort of have a fixed eating rate in this situation, they're going to make up for any shift in population by either a larger shift in population by eating more, or a smaller shift in population by eating less. And as soon as we go up to, you know, so interesting things happen. I mean, frankly, so in this case, we see a small shift. We go to 2, we go to 3. We see that the phase has started to be shifted. Go to 4, and we actually see that now we're getting peaks where we're getting larger peaks in the situation where we have DDT. So we have longer, sort of lower troughs, but then the peaks that we're getting are actually becoming a little bit larger. And if we go up to something like 7 or 8, we see this really interesting thing where, you know, basically instead of having sort of normal cyclic cycles, we will still have normal cyclic cycles, but they'll be much longer. And when the prey comes back in force. And this has actually been observed quite a bit in farming. So this has been observed quite a bit in pest control practices, where they, you know, went and DDT'd everything, and it turned out that what happened was, you know, they actually, you know, they successfully killed the vast majority of the prey, and then there was some predator that was actually doing a lot of the pest control that then immediately died out. And so then when the prey came back, it came back in force. There's also there's some suspicion anyway that this happened with cockroaches in Russia a few years ago, where they gassed them all, and what it wound up doing was killing some predators. So they had a year or two where they poisoned them all, where things were cockroach free, and then they came back several years later and just overran one of the cities. I should find that case study exactly, but so this is interesting. So one of the things that this does is, and this kind of modeling does, is it gives us a laboratory to test these things. But the other thing that it does, and where in particular this DDT example has been important in the past, is give some kind of theoretical justification to what people are seeing, right? So it's easy enough for me to say, oh yeah, well maybe, you know, what happened was that the there were birds that were eating the locusts, and then the birds went away or died when we used DDT, and that's what the problem is. But I mean, there's a million scenarios that we could come up with, and there's a question of, well, okay, how likely is that, right? If you give me a model, is that like in some tiny, tiny percentage of cases, where the parameter values exactly match up and cancel each other out, that's going to happen? Because then that seems very unlikely, right? Nature is much less stable. But if we write down a very simple model and we put the behavior in, and all of a sudden we see what we were expecting come out, then that provides some sort of theoretical justification for the thought experiment anyway. And of course, there's a lot of things we could argue with here. We could say, well, maybe DDT doesn't kill a percentage of the population, right? Maybe DDT doesn't kill a percentage of the population each year. Maybe we should simulate this as, kills a percentage of the population down to 10%, and then it becomes significantly less effective. What happens then? What about size point? Well, what if the population growth isn't unrestricted, right? What if the population growth is actually is logistic? And we can certainly play around with that without too much trouble, right? We can just throw a logistic term in here right now. 1 minus x over. Good. Okay, all of a sudden things seem to be stable. Well, what's going on there? And so there's a lot of different assumptions that we can make in these models, and we can try to use them to say something. But and often we can actually use them to simulate interesting behavior. We'll see a couple more examples on Wednesday. In particular, one example that has been used a lot in ecology in recent years, which is the fact that introducing predators into a competition scenario can actually stabilize a competition scenario that would otherwise result in extinction. But yeah, so I would like you guys, so as you kind of go off and think about this, and I'd really encourage you to read the case studies in the book, as the companion here, to think about, like, now we're kind of solidly in the world of multivariable nonlinear differential equation models. And we can take a lot of these simple models and, with the addition of a few terms or a few situations, start to model some fairly complex behavior. And that's what I want you guys to start thinking about doing for your final project. It can be based on something that we've done in class. It can be based on something that we haven't. Again, if you don't want to do differential equations modeling, feel free to talk to me and we can talk about other things you could do. But yeah, you could take models like this and adapt them to other kinds of situations. One of the big hot topics in recent years, for instance, up until this year, has been using these epidemiological models actually to talk about the spread of information on the internet, and to try to sort of adjust them towards the spread of fake news, memes, secrets, gossip, etc. And so, yeah, just for the next couple of days, just do some thinking about what you might be interested in. And if you have any questions or if you have any ideas, you want to run them by me, feel free to email me or set up a Skype meeting. So yeah, if there are there any other questions?